So this is joint work with my supervisor, Marcelo. Apparently this isn't working. Maybe it just needs to. Yes, it is working. Cool. So I'm going to talk a bit about motivation. Then I'm going to talk about the universal property of quotient syntax. Then I'm going to do some technical devices. And I'm going to talk a little bit about the rock formalization of this work. So motivation is that normalization by evaluation for us is finding a normal form, and in particular in a reduction-free fashion. And that allows us to convert the semantic beta-eta normality testing to alpha equivalence testing. And we associate three correctness properties with this. Soundness, that the output of normal form is convertible with the input, that it converts convertible terms to alpha equivalent terms. And then we also identified the weak form of that property, where it just maintains beta-eta convertibility. Except wasn't this solved over 20 years ago by Torsten, by George, and by my supervisor, Fiore? Yes, but there's a number of problems with each of their approaches. So Torsten's approach with Hoffman and Stryker is only partially categorical. There's some ad hoc techniques. It does require an ad hoc analysis of normal forms, although we can argue about how ad hoc it really that is. And it doesn't make much use of universal properties, but it does establish full correctness. It does establish both soundness and strong completeness. Chubik et al.'s work is fully categorical. It doesn't make any ad hoc analysis of normal forms. It does make use of universal properties, but because of the lack of ad hoc analysis about normal forms and its universal property, it only produces partial correctness categorically. So it only establishes soundness and not strong completeness. So it doesn't really even solve the goal, and they resort to non-categorical techniques to prove the results in their setting. And then my supervisor's work, again, it's fully categorical. It uses ad hoc analysis of normal forms. It doesn't use a universal property really, but it does establish full correctness. My new approach is fully categorical. There is no ad hoc analysis. It does make of universal properties and is fully correct. So we present a slick new categorical construction of normalization by evaluation with full correctness for the simply typed lambda calculus. And so where we start is the free Cartesian closed category over a single base type. Yes? Do we have
sums?
No, we don't use sum types. I'll get to that in proposed later work. And so the way we look at what it means to be the free Cartesian closed category is a kind of initiality property, where for any Cartesian closed interpretation functor I into some model M, we can establish a stricter interpretation functor that is canonically naturally isomorphic. And from this, we can define an I-theoretic or M-theoretic normalization function that allows us to take in a substitution or even an individual term in our category and produce some embedding of that or some transformation of that term into category M. And from this, we can derive soundness purely based on naturality of Q and U and the fact that they form a natural isomorphism pair. Quite a nice short proof. But it only establishes weak completeness in that we can only relate the output morphism as M relates or understands morphisms to be related. So in particular, it would only give us that it maintains beta-eta conversion rather than producing alpha equivalent terms, although observationally it does do that. And so we can go to some choices of our functor I. The identity functor doesn't work for normalization, but the Yoneda functor does, and that allows us to find a normalization function. And here's a bit of lying in that this normalization function would give you a natural transformation between Yoneda of gamma to Yoneda of delta. So we can instantiate that at gamma and then apply the identity substitution to actually get our final term out. But then to improve on this, we need to introduce some more technical devices. So I introduced the concept of a Cartesian pre-closed category. And a category is such that when it is Cartesian, and it has this operator on objects that's kind of similar to what you would see in a fully Cartesian closed category, but we only require weaker conditions on it existing, and that we only require natural maps rather than a natural isomorphism pair. And we have a notion of a Cartesian pre-closed functor, which curiously is a heterogeneous notion in that it maps from a Cartesian pre-closed category C to a fully Cartesian closed category D, and we'll see why that's useful later. And we require that it weakly preserves the pre-exponential structure. And so E tilde has to satisfy some property, but it's not given on the slide, but it's related to the properties you would normally see for a normal preservation of Cartesian closure. And so this allows us to expand our perspective and give us a free Cartesian pre-closed category, which is then just the category of context and substitutions related only up to alpha equivalents. And so it's a much more intentional view of the terms within the category. And again, that has a similar universal property, and we get a pair of natural transformations there. And we're also going to need a category of renamings, which is just variable for variable substitutions. And we have a pair of Cartesian and identity and objects functors here of the inclusion of renamings into the free Cartesian pre-closed category and the quotienting of the pre-closed category into the fully closed category. And now we can expand our view on normalization a little bit further, making use of the nerve of J, which is given here, which curiously is a Cartesian closed functor quite magically. But again, this still doesn't really help because this will only produce terms in our category F, which relates its morphisms up to beta eta conversion. And so we need to give a stronger universal property for this quotient functor J. And so we start off, it's an initiality property, so we can have J on the left-hand side of our diagram. And so therefore, for any module M and Cartesian pre-closed functor I, we induce a Cartesian closed interpretation functor, which up to renamings gives us a pair of natural transformations. And with this, we can then redefine a new normalization using the Q tilde and U tilde natural transformations instead, with a similar story. However, we now can't establish soundness in exactly the same way that we did before, because we have the Q tilde and U tilde are only natural with respect to renamings, which was the top of that pentagon diagram, and not natural with respect to all substitutions. So we can't commute either the Q tilde or the U tilde past the interpretation of our substitution sigma. However, we still maintain the weak completeness property because it just maps into morphisms in the category M, so it will still relate morphisms as M does. And so we can have some choices of functor here. The quotient functor doesn't work for exactly the same reasons the identity functor didn't work in the fully closed setting. But we can use the Yoneda functor, which is our first and primary example of a Cartesian pre-closed functor, which is why we have a fully Cartesian closed codomain, but only a pre-closed domain. And then when we pick the Yoneda functor, because the Yoneda functor is valued in sets that only relate up to alpha equivalents, we do then obtain strong completeness of our normalization function. So this kind of gives us the normalizer's dilemma. We can have soundness, but no strong completeness, or we can have strong completeness, but no soundness. Unfortunately for normalization, I like to have my cake and eat it, so I'm going to have some gluing. And it suffices for the result, although you can be a lot more precise about how this works. It suffices to use the arrow category of pre-sheaves over the free Cartesian pre-closed category. And we can have an interpretation functor. That's just my weird notation. But in the domain part, we act like the Yoneda embedding. And in the codomain part, we act via the action of J on morphisms. So in the domain part, we have strict information. And in the codomain part, we have weaker information. And so this gives us two normalization functions. We can either normalize in the domain part of the glued category or the codomain part of the glued category. And we can deduce the following properties about this, that we have that the domain part is strongly complete because it lives in the category A, which relates by alpha equivalence. We have that the codomain algorithm is sound because it lives in the quotiented by beta eta conversion. And with some gluing magic and a few uses of universal properties, we have that they agree extensionally, and so therefore we can conclude that the domain algorithm is sound, and therefore the domain algorithm satisfies our full correctness properties. So all this work has been fully formalized in ROC, and we use a variant of category theory called P-category theory, which is where the HOMs, instead of being setoids, we might use an E-category theory, are subsetoids, where you only use a partial equivalence relation, where you've lost global reflexivity. We use the S-prop universe for the evaluation of our pairs. It makes everything go much faster, and it finesses all the problems about double involution of opposites of categories not being convertible with the original category. And this gives us an effective normalization procedure for terms and substitutions. And we use de Bruijn indices, use representation variables, and we aren't very clever about how we do this, so it's probably really slow, but it's a result that we can then go ahead and implement it a bit more efficiently. In future work, we should really analyze the natural of Q tilde and U tilde more carefully. They're only natural, we've only established their naturality with respect to the Cartesian aspect of renamings. We hope to connect it more closely with traditional doing techniques, particularly with those of my supervisor, and lift it to co-products, where because we don't need to think about neutral normal forms, we might be able to finesse some of the problems of co-products and then eventually lift to non-simple or dependent type theory.